Right, so the objective of the task team on the second slide is to deal with this important question about cloud detection. Cloud detection, as we've seen, can be an issue in various retrievals. William was suspecting some cloud detection in the last presentation, for example, in some of the NOAA data, particularly some of the CCI data on the NOAA VHR satellites. And so we know that cloud detection can affect SSTs adversely. Our priority areas for the task team are twofold. One is that, as well as missing cloud, there is a persistent problem of many cloud detection schemes overflagging frontal features, and that's of significant concern to the feature fidelity task team with whom we cooperate. And another area of priority that had been set a couple of years ago was coastal zone cloud detection. Go to the next slide, please. The members of the task team are shown here. I'm grateful to those who've submitted updates for this particular report. We have three updates. That's on the next slide. One from Steinar Eastwood, one from Claire Bilgin, and one from Min-Kun Liu. So I'll start off with Steiner's update, please, which is on slide number 5. Great. So Steiner has been working within a project called CIPHER-MAST, which is a Copernicus project, looking at both sea surface temperature and ice surface temperature product quality, focusing on the sea and land surface temperature radiometer, SLSTR. And on cloud-related issues in the past year, the idea has been to look at cloud masking using a scheme that's from the now casting SAF, which is a EUMETSAT consortium, to see whether this cloud masking can be improved, particularly over sea ice regions. So I think an interesting aspect of this work is the validation of cloud detection or cloud absence using Calliope cloud radar, as well as sign-up observations of clouds. Steiner hasn't given me a lot of detail on what he's found. This is more or less an advert or a full presentation that he'll be giving at the Sentinel-3 validation team meeting in December. Next slide, please, Karen. Thank you. This is also, in a sense, a bit of an advert. At a previous GRIS meeting, the task team reported work led by Claire Bilgin, again working on the SLSTR radiometer, where we've been focusing on this issue of overflagging of false detection of cloud in coastal zones. Next slide, please, Karen. This is an example. So coastal zones, over coastal zones, the ocean is often brighter than it is typically in the open ocean because of turbidity from either the runoff of the land or from phytoplankton in the water. So this is an example of a couple of locations off the coast of China and off coast of Korea, where you see that in the SLSTR operational cloud detection, there's very significant areas of water that are quite obviously, when you look at the image on the left, the reflectance image on the left, quite obviously clear sky, being flagged as cloudy because the waters are relatively bright. And this is essentially because of the use of reflectance channels. And as with any cloud detection issue, there's always a trade-off. If you essentially make yourself less sensitive to bright water, you're also making yourself less sensitive to thin cloud and cloud edges. So how's that trade-off going to be resolved? Well, in this study, we were able to take advantage of the fact that the SLSTR obtains visible reflectance imagery at a higher resolution than it does thermal imagery. And so we have the ability to see the variability of the reflectance within the area of a single thermal pixel. And clouds are more variable in space than the sorts of turbidity variation that we see in the open ocean most of the time. And therefore, by looking at this reflectance variability within the area of an infrared pixel, this effectively replaced the use of just the reflectance itself as a threshold. Instead, we were looking at the standard deviation of reflectance over that small area. And this is extremely effective in coastal zones. And also avoids, it also reduces the dependence on thermal spatial variability, which enables cloud features to be more finely resolved, as shown in the lower plots as well. So that paper is now published. You saw the reference in the previous slide for anyone who wants to read further on that. Next slide, please. So the final report comes from Minkun Liu at the Ocean University of China. And Minkun has been working on cloud detection for HY1C, the colour in ocean temperatures. I can't quite remember what COCTS means. It's a mixture of ocean colour and a temperature. And the idea here has been to try to improve the cloud detection model and especially the cloud detection of cloud edges using a machine learning approach. Machine learning approach, you have to choose what your input features are going to be, and those are listed on the left in the picture. And it's the usual sorts of observations that we'd expect for cloud detection, plus a few others, such as latitude and longitude. You also need a truth, because a machine learning approach needs to be trained against something that you regard as being a truth. And in this work, Minkun has used the results of a Bayesian algorithm, so that's a probabilistic method of inverting the probability of clouds using simulated and observed radiances, but has augmented this by manual checking and by manual labeling to make that result a bit more reliable, because after all, there is no perfect cloud detection algorithm presently. So that's as ground truth. And the details of the design of the machine learning model, I'm not in a situation to be able to go into that in detail, but I know that Minkun is working on a paper that those who are interested will be able to read when it's published. What I wanted to show, what I wanted to emphasize was this interesting aspect, enhance the performance of the machine learning model. She's detected the edges of clouds and used that as part of the learning. And this is quite a smart thing to do, because it's often the edges, the cloud edges, where some cloud contamination creeps through into the SST. Next slide, please, Kara. So here are some results. There are RGBs of the cloud field on the left, as well as an 11 micrometer, a column of 11 micrometer brightness temperature images. And you can see the Bayesian cloud truth that's being used as the training, and then the prediction. In fact, not as training, as testing data here. So we have, obviously there's been a training data set, but this is now an independent testing data set. The comparisons are shown in statistical form on the right, and we have very impressive degrees of agreement between the machine learning based algorithm and the ground truth, which was Bayesian plus inspection. I have to say, in the experience of looking at comparisons of cloud detection algorithms, that these are extremely comparable statistics between the two forms of retrieval. And so this looks very promising. And I do think this idea of training with an emphasis, an extra emphasis on cloud edges to make sure that those are well trained for, is possibly contributing quite a lot to the good results that are shown here. So I think this is definitely something to work on in the future. And to the final slide, please, Yara. Okay, great, thank you. So in terms of the future of the task team, I do need to hand over the leadership of the task team. I've been letting the team down somewhat in the last year because of some additional responsibilities I've taken on another project, a climate information service for the UK. So I'm looking for a replacement chair, and I'm speaking to a couple of people about that, but also open to anybody else who's interested. Now, of course, a future chair would then set a set of new plans in the next year, but I will give you my opinion about what themes I think are likely. I think the issue of high resolution sensors, we've heard about the Trishna emission that's coming up, and that will also be highly relevant to coastal zones. And there's been interesting work in the Expo team about the improved exploitation of temporal change for cloud masking, and I'm sure this could be taken further. And then lastly, I think Min-Kun's shown that there are probably things we can learn from machine learning enhancements to cloud detection, although I'd always want to have those physically based in some way. So thanks very much.